Hello everybody, this is Math 145, day 11. We're talking about lesson 9, trigonometric identities today, especially the addition formulas. Those are two formulas that really come out of left field, out of the blue. I don't think that anyone just picked at random would discover them. But they're still important. I want you to remember them. They're absolutely on the syllabus. And because we're having this online class, I'm going to do something which is actually not really possible, which we don't have time for in a face-to-face class. I'm going to show you how one can justify this, how one can retrace the steps of someone discovering this formula. And that is not rocket science. That's quite possible. It's a nice exercise in trigonometry, just perfect for a short video clip. So I don't expect that you can produce that by yourself. I'm not sure I would have found this, but retracing the steps is great fun. So we're starting with two angles, alpha and beta. You make a chain of right triangles. Let's see, base, make alpha pretty small. And we can go right triangle. And then put beta on top, make that nice and big. And we want to make another right triangle with the right angle here. Oh, actually, that's not right enough. A little longer. So we need to make this line all the way up to there. And then complete this figure to a rectangle. By which I mean, we continue this straight up until we are at this level. We go straight up here and then go across horizontally so that we have a rectangle. Those quarter circles with a dot indicate right angles. And this was supposed to be the angle beta. Alpha and beta are given, and we'll just make this figure, and then we choose a unit. And for that, I want to put labels A, B, C, D. Is my rectangle. Let's call this point E, that point F. And this is the surprising part. Choose a unit, the length of AF. So this line segment, we choose that as a unit. From now on, it will have length 1. After we've done that, we can express pretty much every other line segment in this figure in terms of alpha and beta trig functions of them. For example, the right triangle AEF has beta in it, and that leg is the sine of beta. The other leg is the cosine of beta because it has hypotenuse 1. Express legs of AEF in terms of beta. And then we can get to work on triangle ABE. Legs of that triangle. Expressed in terms of alpha. So over here is this sine alpha times the hypotenuse. Sine alpha times the cosine of beta. I'm going to say squeeze this underneath, but it's a times, okay? It's multiplication. Hypotenuse times the sine of alpha. And the other leg, the longer leg, is the cosine of alpha times the hypotenuse. All right. Next, we want to chase down the angles at E and at F. So at E, we are having an angle which is 90 degrees minus alpha. I just dotted that one. So the scientific notation for angles would be first a point on the first side, then the vertex, then a point on the second side. So this is A, E, B. A is the vertex. First side has A on it and the second side has B on it. So AEB is this angle. It has measure pi over 2 minus alpha. Then the angle, the other one at E, first side has F and the second one has C, am I right? No, otherwise C and then F. C, E, F is this one. As measure, pause the video, 30 seconds. What's the measure of that angle? We just said there's a pi over 2, 90 degrees minus alpha here. The first one that I dotted. The next one, the middle one, is a right angle, and then comes this angle that I'm asking about, CEF. It has measure alpha. I'll give yourself a pat on the back if you saw that. Then we can figure out a bunch more because now we've got another right triangle, ECF, top right corner with alpha in it. And so at F, we're seeing another angle of measure pi over 2 minus alpha. So that is E, F is the vertex, and then C as measure 90 degrees minus alpha, or pi over 2 if you're measuring in radians. Okay, what is the middle one at F? That has still vertex F and starts with A, then F, then E, so it is this one. Let me do 2 dotted lines for that one. That's pi over 2 minus beta. So we have pi over 2 minus alpha, pi over 2 minus beta. And the third one, I'm going to give that a name. That's an important one. We'll call that one gamma. What can we say about gamma? The measure of this plus the middle one, pi over 2 minus beta, plus pi over 2 minus alpha, the one on the right, all add up to 180 degrees, or pi, working in radians. Okay, we can cancel out a pi on both sides, and we get gamma minus beta minus alpha is 0. In other words, gamma is equal to alpha plus beta. Okay, back to the figure. We have yet another right triangle, this one with gamma in it. That's AFD. So what we're seeing is the sine of gamma on that vertical side AD. And this is what we're after. All right, we can see the sine of alpha plus beta, and that's the length of AD. Because we have a rectangle, this is equal to the length of BC. Let's write that down. And BC is, of course, BE plus EC. EC is the only piece of the puzzle that is still missing, that we haven't figured out yet. But that's part of a triangle, a right triangle with hypotenuse sine beta and an angle alpha. So this is sine beta times cosine alpha. Sine beta cosine alpha, the other one was sine alpha cosine beta. Let's write that down. Sine alpha cosine beta, and the other one is cosine alpha sine beta. And that is called the addition formula for the sine. Sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Deserves a red box. Obviously enables us to calculate a whole bunch of new sine values, and I'll do an example in a minute. But I should mention that there's a sister formula for the cosine of alpha plus beta. Going back to the picture, the cosine of gamma is, of course, df. Back. df, that line segment, is the cosine of alpha plus beta. And express that in terms of our trig functions And it's of course DC minus FC and you get the addition formula for the cosine. Cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. That deserves its own red box. Those two formulas are basic. Notice the patterns in there, the kind of X pattern with the sines and cosines switching places for the sine formula, and the kind of parallel pattern, cosine cosine versus sine sine with a negative sign in the middle for the cosine formula. So it's kind of nice looking formula, and you really should remember those two. And then there's Pythagoras, and from those three formulas comes everything else that we need to know in terms of trig identities. Everything else. There's a whole bunch that comes out of this, but those three, Pythagoras and those two formulas, are the ones that are crucial. For example, the tangent. Here's a consequence. Take the addition formula for the sine and divide both sides by cosine alpha cosine beta. So I get sine of alpha plus beta divided by cosine alpha cosine beta equals sine alpha. Cosine beta will cancel out, so that's just cosine alpha left, plus cosine alpha will cancel, and sine beta divided by cosine beta is left, which is of course tangent alpha plus tangent beta. Next, let's divide cosine of alpha plus beta by the same amount. So that gives me cosine alpha cosine beta divided by that, that's 1, minus sine alpha sine beta divided by cosine alpha cosine beta. That's 1 minus tangent alpha tangent beta. And now divide one of those equations by the other, and you get the tangent of alpha plus beta is tangent alpha plus tangent beta. That's the first equation, divided by 1 minus tangent alpha times tangent beta. So we have a nice addition formula for the tangent, which comes right out of the addition formulas for sine and cosine. Nicer. Nice red box. And let's do applications in a separate video because this is getting kind of long.